Hey everyone, in this video we'll discuss and explain the different physical properties of elements depending on the position in the periodic table. First of all, I want to define physical properties and explain the difference between physical and chemical properties. In chemistry, physical property of a substance refers to characteristics and properties that can be measured without changing the underlying identity of the substance, that is, without altering the chemical composition of the substance itself. In contrast, chemical property is more better defined as the substance's ability to undergo a chemical change, and chemical change refers to chemical reactions that will change the substance identity or chemical composition. In this video, we'll focus on physical properties of different elements, and you'll realize that the physical properties ultimately depend on the chemical structure of the element or the compound. In this video, we'll go through the following examples of physical properties: melting and boiling points, the appearance of the substance, density, conductivity of both electricity and heat, the strength and hardness of the material, malleability and ductility, and finally, solubility. The position of an element on the periodic table heavily influences its chemical structure, which then in turn affects its physical as well as chemical properties. Majority of the elements on the left and middle part of the periodic table are classified as metals, with the exception of the first element, hydrogen, which is a non-metal. On the right-hand side of the periodic table are the non-metals, shown in yellow, and in between the metals and non-metals, there are a few elements referred to as metalloids or semi-metals. The distribution on the periodic table can be seen as a ladder-like structure, which includes first element as boron, silicon, germanium, and more rarely, arsenic, Sb, and Te. The more common semi-metals will be the ones earlier on in the periodic table, which includes boron, silicon, and germanium. So the metals are primarily on the left and middle part of the periodic table. The non-metals are on the right-hand side, with the semi-metals or metalloids in between them. Knowing the type of element and its position in the periodic table is important because different types of elements will form different types of chemical structures. Metal elements tend to form a structure called metallic lattice. Semi-metals will form covalent bonds to form a continuous network called covalent network structure, and non-metals can form either one of the two structures, either covalent molecule or network structure, similar to semi-metals. In chemistry, the word lattice or network in the context of chemical structure refers to when a group of atoms are connected via bonds or attractive forces in a continuous manner that forms a gigantic network without having a finite number of atoms. In a metallic lattice, the electrons of the metal atoms are no longer orbiting each atom and they become delocalized, meaning they can move anywhere along the entire lattice structure. As a result, the metal atoms become metal ions, acquiring a more positive charge due to the loss of their intrinsic electrons. The entire metallic lattice is held together by the attractive electrostatic forces between the negative electrons, which are delocalized, and the positive metal ions, which are arranged in an array or layers known as a lattice. Semi-metals and non-metals can form a covalent lattice, also known as a network structure, whereby each atom of the non-metal or semi-metal is connected to one another via multiple covalent bonds. When the atoms are connected via this way, they can form a large network that's similar to the metallic lattice that we saw here. The only difference is that in a covalent network, the atoms are connected via covalent bonds, and they do not have any delocalized electrons. This will be an important difference in explaining the different physical properties later on. Ionic lattice is very similar to the previous two. This is the chemical structure for an ionic compound, which consists of two or more ions from different elements. Here, the red and blue circles represents the ions that have positive and negative charges respectively. Due to their opposite charges, they are connected and held together via strong ionic attractions, that is, electrostatic forces between the positive and negative charges of the ions. Ionic lattices will be discussed in a separate video under the topic of ionic compounds. Non-metals can either occupy a covalent molecular structure or covalent network structure. The similarity between molecules and network structures is that in both structures, the atoms are connected via covalent bonds, that is, a sharing of electrons from adjacent or neighboring atoms. However, an important difference between them is that in molecules, there's a finite number of atoms of each element. For example, in hydrogen-2 diatomic molecules, there are specifically only 2 hydrogen atoms. One collection of these 2 hydrogen atoms is referred to as a hydrogen molecule. These molecules are held together by relatively weak intermolecular forces. In contrast, the covalent bonds in a network structure connect the atoms, such as in this case carbon, in a gigantic and much larger network where there isn't necessarily a finite and predetermined number of atoms of carbon. This diagram merely shows a section of the network that's formed by connecting the carbons via covalent bonds in this way. In a covalent network structure, the atoms are bonded together by relatively strong covalent bonds rather than intermolecular forces. Again, this is a major distinction that you need to understand because it explains the different physical properties between the 2 types of covalent substances, as we will explore later on. The first physical property we'll look at is the melting and boiling points of substance. These refer to the temperatures at which the state of matter of a substance changes. The melting point refers to the temperature when the solid transitions to a liquid state, and the boiling point refers to the temperature at which a liquid transitions to a gaseous state. The melting and boiling point depends on the pressure that's applied on a substance, as well as the allotropic form of the elements, especially for covalent substances. This diagram shows you the rough distribution and variation in the melting point of elements depending on the position in the periodic table. The redder the element is, the higher its melting point, and the more blue the element is, the lower its melting point. Now you can see metals tend to have the highest melting point out of all the elements, primarily situated in the middle of the periodic table in the transition metal group. The only exception to this rule is the element carbon, which is considered as a non-metal. The rest of the non-metals, hydrogen, and most of the elements on the right-hand side of the table tend to have lower melting points. Metals in general are mostly solids at room temperature and pressure. There are some exceptions, however. Mercury, element symbol Hg, is in fact a liquid at room temperature and pressure. The melting point of mercury is -38 degrees Celsius. In contrast, tungsten, element symbol W, has a much higher melting point of 3400 degrees Celsius. So you can see, although metals are mostly solids, and their melting points are usually above the room temperature, there is a wide variation in the melting point of metals. This is primarily because metals, although they all form metallic lattice structures, the organization and the strength of attraction within these metallic lattices vary quite a lot, depending on the metallic element itself. Semi-metals are solids at room temperature, and they consistently have relatively high melting points. For example, germanium has a melting point of almost 1000 degrees Celsius. So there's lesser extent of variation in melting point of semi-metals compared to metals. In contrast to metals and semi-metals, non-metals tend to be mostly gases, but they do still have a variation in their melting point. The main difference is that non-metals which occupy a covalent network structure tend to have higher melting points. A notable example of this is an allotrope of carbon, which is diamond. Diamond has a melting point of 4000 degrees Celsius, even higher than the melting point of tungsten. In contrast, non-metals which occupy a covalent molecule structure have lower melting points. For example, hydrogen gas has a melting point below 25 degrees Celsius at a -26 degrees Celsius. So most of the time, non-metals which occupy a covalent molecular structure will be gases, if not liquids, at room temperature and pressure. The difference in melting point between the two different types of non-metal structures is due to the difference in bonding and attractive forces that hold the structures together. Recall that in covalent network structures, the atoms are bonded via stronger covalent bonds, which require more energy to separate when transitioning from a solid to liquid state, hence the higher boiling point in these covalent network structures. In contrast, covalent molecules are held together by much weaker intermolecular forces, which require less energy to separate when transitioning from solids to liquids, hence the low melting point of these type of non-metal substances. I discussed the different types of intermolecular forces for these covalent molecules in its own video. The appearance of a substance is also one of its physical properties, and can be useful in distinguishing between whether the elements are metal, semi-metal, or non-metal. Generally speaking, metals have a shiny and lustrous appearance due to the fact that the localized electrons in the metallic lattices are able to absorb and release light, allowing some of the light to be reflected, giving its shining appearance. Non-metals appear very differently to metals. They have a dull appearance, and semi-metals tend to appear in between metals and non-metals. Some semi-metals like germanium may come off as shiny and lustrous, and sometimes may be mistaken as a metal. But most semi-metals will be less shiny compared to metals, and of course, more lustrous compared to non-metals. The density of a substance is its mass divided by the volume it occupies. Density depends on the temperature, pressure, as well as the allotropic form of the element. Not to mention, density also depends on the state of matter of the substance. The solid state of the substance consists of atoms or molecules that are more tightly compacted, resulting in the same mass occupying the smallest volume possible. So this is where the density is the highest. As a solid state transitions to liquid to gases, the same amount of atoms and molecules will start to occupy a greater volume, which leads to a decrease in density. The gaseous state of a substance will have the highest density out of all three states. This periodic table shows you the distribution of density between different elements. Again, you can see metals tend to have higher density, with some of the metallic elements in the transition metal group having the highest density. Non-metals, which are hydrogen and the ones on the right-hand side of the periodic table, tend to have the lower densities because they primarily occupy as gases at room temperature and pressure. Now, even though we saw that some metals have the highest density of all the elements, metals in general actually have quite a variable density. As an example, aluminium, which is a common metal that we find in some of the appliances like aluminium cans or foil, have a relatively low density for a metal at 2.6 grams per cubic centimeter. Tungsten, on the other hand, has a much higher density of 19.3 grams per cubic centimeter. So if we have the two same cylindrical blocks of the two metal elements, they occupy the same volume, the tungsten may weigh 1 kilogram compared to 150 grams in aluminium. This is more than 6 times different in their mass. Semi-metals have a smaller variation in density. They tend to consistently have higher densities on average. For example, germanium has a density of 5.2 grams per cubic centimeter. Non-metals also have variable density. And again, the main distinction lies between whether the non-metal occupies a covalent network structure or covalent molecular structure. The ones that are in covalent network structures will have higher density. Again, diamond, being an allotrope of carbon, occupies a covalent network structure, has a density of 3.5 grams per cubic centimeter, which is relatively high for a non-metal. Covalent molecules, on the other hand, tend to have a lower density. For example, hydrogen gas has a much lower density of 0.09 grams per cubic centimeter. The electrical conductivity of a substance refers to how well it conducts electricity. Electricity refers to the movement of any charges within the material. Most of the time, these charges refer to electrons, which are the negative charges that are found in atoms. So how well these negative charges will move through a medium of material is its electrical conductivity. Now, out of all three types of elements, metals are the best at conducting electricity. This is because the metallic lattice structure is unique in that they contain delocalized electrons, which are mobile. These electrons initially belong to the metal atoms, but when the metal atoms form this continuous gigantic metallic lattice, the electrons that are originally in the valence shell become delocalized, meaning they can move anywhere they want. So when you apply a potential difference, that is, when a positive end and a negative end to a metal, these delocalized electrons will all move towards the positive end of that potential difference, resulting in a flow of these electrons, which is electricity. So metals, because the chemical structure contains this sea of delocalized electrons, they tend to be very good electrical conductors. Now, in contrast Non-metals are mostly insulators. They are not very good at conducting the flow of charges, as they contain no mobile electrons in their chemical structure. Now, the exception to this is a notable example of an allotrope of carbon, that is graphite. Graphite is actually quite a good electrical conductor because it contains mobile electrons. Now, I talk about the chemical structure of graphite and why this is the case in its own video on the allotropes of carbon. Otherwise, majority of nonmetals, whether they occupy a molecular or network structure, they are mostly poor conductors of electricity. Semimetals, the conductivity of electricity actually varies. Silicon and germanium are very famous semimetals that can be made into semiconductors, but usually this requires modification of the elements. So pure form of silicon and germanium are not very good at conducting electricity until they're modified in their unique processes to become semiconductors. Even when they become conductive, semimetals are worse than metals at conducting electricity, but they are better than most nonmetals. So again, they display that intermediate property between metals and nonmetals when it comes to electrical conductivity. Thermal conductivity refers to the conduction of heat. It is measured by the rate of heat transfer through a particular substance or medium. Now, what is heat? Heat refers to the transfer of energy from a high to low temperature. So if we have a block of material here, one end has a high temperature and one end has a low temperature, so hot and cold. Heat transfer refers to the movement of energy from the high temperature end to a low temperature end. Heat transfer depends on both the movement of charges, including mobile electrons, or the vibration of atoms inside the chemical structure of the element. So in this diagram, you can see as the heat is applied, it causes the atoms of this network structure to vibrate, and the vibrations will help transmission of this energy from one end to another. Thermal conductivity measures how quickly this heat transfer occurs. As a general rule, substances and materials that are good electrical conductors also tend to be good thermal or heat conductors. This is because electrical conductors, they rely on these mobile electrons, which can also help and facilitate heat transfer. This is the reason why metals are both good electrical conductors as well as good thermal conductors. Non-metals, on the other hand, similar to electrical conductivity, they are mostly insulators when it comes to conduction of heat, with the exception of graphite, which is an allotrope carbon. Graphite is also a good thermal conductor. The thermal conductivity of semimetals also varies. Some semimetals may be better than the others at conducting heat, but when you compare them to metals, they're definitely inferior when it comes to conduction of heat. And when you compare to non-metals, they're better at conducting heat. So again, they display that intermediate property when it comes to thermal conductivity. The tensile strength of a material refers to how much and the amount of stress that can be applied to it before it deforms permanently or breaks apart or fractures. So in other words, how much force can it withstand before breaking apart? That is the tensile strength of the material. Metals tend to have higher strengths compared to other types of elements. Semimetals have variable strengths, again intermediate between metals and non-metals, and non-metals have variable strengths. But generally speaking, they have the lowest strength out of all three types of elements. But if you're comparing between the two, covalent network nonmetals have higher strengths compared to covalent molecules. I want to make a special mention of the element titanium, which is one of the metals with the highest strength to mass ratio. Metals with high tensile strength, we tend to use them in a variety of different applications, such as in engineering, medicine, jewelry. And titanium is one of the most suitable elements because it gives relatively high strength for low amounts of mass or weight. The hardness of a material refers to its resistance to surface deformation, indentation, or scratching. There's different ways we measure hardness depending on the mechanism of experimentation. So whether we cause it to deform at the surface, indentation, or scratching. Keep in mind, this is slightly different to the tensile strength because tensile strength is all about how much force can it withstand before breaking apart or deforming permanently. The goal of measuring hardness is not to break the material, but to see whether we can cause that surface deformation, such as the indentation or scratching. Unfortunately, for hardness, there's no general trend amongst elements. Especially for non-metals, the hardness varies quite a lot and it depends on the specific allotropic form of that particular non-metal element. There are many ways of measuring hardness. Notably, Mohs hardness measures the scratch resistance. This is outlined by the graph here, where it's measured from the highest value of 10 to a lowest value of 1. A material with a higher hardness is able to scratch and cause surface deformation of a material that has lower Mohs hardness. So for example, if we scratch the surface of diamond versus talc, which has a hardness of 1, the diamond surface would not be deformed, whereas the surface of talc would cause significant scratching due to the diamond's hardness. There are other scales that measures indentation resistance, specifically in metals, for example, the Brinell and Vickers hardness, which I won't speak about in this video. Metals have a variable hardness. For example, tungsten has one of the highest hardnesses for metals at 7.5 on Mohs scale, whereas lithium has a much lower hardness of 0.6. So that means tungsten is much harder to cause surface scratching or indentation, whereas lithium is much easier to do so. Semi-metals have relatively high and consistent hardness. Germanium silicon have very similar hardness at 6 and 7 on the Mohs scale. Non-metals have variable hardness, and again, it depends on whether it occupies a network structure or molecular structures. The network structures tend to have high hardness, notably diamond, which has an extraordinarily high hardness for a non-metal at 10 Mohs scale. This is the highest number that we can assign on the Mohs scale. In contrast, non-metals that occupy a covalent molecule structure tend to be soft or low in hardness. For example, sulfur tend to be a powder, has a Mohs scale of 2. The malleability and ductility of a material are often discussed together, but there's one small difference. The malleability refers to the ability of the material or substance to deform under compressive stress or force without causing it to break apart or fracture. A material is usually described as malleable if it can be hammered into sheets like these metal sheets here without breaking apart. Ductility, on the other hand, refers to the ability of the material to deform under tensile stress without fracture or breaking apart. A material is described as ductile if it can be drawn or stretched into these wires as shown here. These two terms are generally used to describe metals. This is because metals are generally malleable and ductile. When we apply either a compressive or a tensile stress to the metallic lattice, we are essentially shifting layers of the metallic ions against each other. This actually doesn't disturb the intrinsic electrostatic attraction between the positive metal ions and the surrounding negative electrons. Because as you're shifting them across, the negative electrons are still delocalized. They are still surrounding the metal ions. So when the force is applied in both compressive and tensile manner, the electrostatic attraction within the metal lattice is maintained, allowing the metal to be malleable and ductile. Now, as a general rule, most metals are both malleable and ductile. Lead, element symbol Pb, is one exception to that. Lead is malleable, meaning it can be compressed into metal sheets without fracture, but it is not ductile. We don't usually draw lead into thin wires like we do for most other metals. So a metal can be malleable but not ductile. The converse is not true, however. Most of the time, if a metal is ductile, it tends to be also malleable. Semi-metals and non-metals, which are covalent substances, are brittle, meaning that if we apply a small amount of force or stress, whether it's compressive or tensile, they will break apart, they will fracture. This is described by the word brittle. So malleable and ductile are usually used to describe metals, and we use the word brittle to describe semi-metals and non-metals, whether or not they are in covalent network or molecular structures. Finally, let's talk about the solubility of an element. Solubility refers to how well an element can dissolve within a solvent. This depends on the nature of the solvent, whether the solvent is polar, for example water, or non-polar, for example oil. Metals and non-metals, they cannot dissolve in solvents in general. Doesn't matter whether it's polar or non-polar. They simply lack that interaction with the solvents due to their strong lattice network structures. Recall that metals occupy a metallic lattice and semimetals occupy a strong covalent network structure. Similarly, nonmetals, which occupy a covalent network structure, like graphite and diamond, which are both allotropes of carbon, are generally difficult to dissolve in solvents, regardless of their polarity. Covalent molecules have variable solubility in polar and nonpolar solvents. The general rule is polar molecules will dissolve in polar solvents, like water. Nonpolar molecules tend to dissolve in nonpolar solvents, like oil. And there are some molecules which have intermediate solubility, allowing them to dissolve in both types of solvents. These are generally regarded as surfactants. So when it comes to solubility, we generally only use this to describe covalent molecules, because only covalent molecules will display some degree of solubility depending on whether it's a polar or nonpolar solvent. This concludes the video on physical properties of elements. Hey everyone, if you found this video helpful, smash that like button and don't forget to subscribe. Want even more? Become a Patreon member for early access to videos, exclusive Discord discussions about questions on chemistry and physics, and live preparation sessions for your exams. Don't forget to head over to our website for topic tests and practice exams to further improve your understanding and learning.